where James Urban and Doug Merkler will be discussing the basics of designing for trees and soils in desert areas. My name is Lita. I'm the creative director at Deeproot, and I will just be walking through a few quick items before we get started. We are recording the webinar. A link to it will be sent out later today to everybody who attended as well as everybody who registered and wasn't able to attend. So please feel free to forward that link around if you know anyone who wasn't able to make it. In addition to that, attendees will be muted throughout the presentation. We're going to try to keep the presentation to about 45 minutes so that we have time at the end for questions. If you do have any questions, feel free to submit them at any time using the chat box in the control panel on the right-hand side of your screen. At the end of the presentation, I'll be scrolling through those and reading them aloud so that everybody can hear Jim and Doug's responses. So with that out of the way, let me introduce our presenters. Jim Urban specializes in the design of trees and soils in urban spaces. He has written and lectured extensively on the subject of urban tree planting and has been responsible for the introduction of many innovations, including most of the current standards relating to urban tree plantings. Jim was awarded the 2008 ASLA National Medal of Excellence for his contributions to the profession, and he is the author of Up by Roots, Healthy Soils and Trees in the Built Environment. Doug Merkler is a fourth-generation Nevadan and a resource soil scientist for Nevada with the USDA Natural Resources Conservation Service. His great-grandfather settled in the Elko, Nevada area in 1877, establishing what was to become one of the larger sheep ranches in Nevada. Doug was awarded the Soil Scientist of the Year nationally for the USDA in 2004 and is currently involved with the Technical Soil Services Program for Nevada. So with that, we'll begin, and I'm going to make Jim the presenter.
Okay.
Jim and Doug, take it away. We can see your screen.
The question, Lita, do you have the images up, or are you just seeing my big screen here?
I can see your desktop with your presentation up, and now I see it big. That's perfect.
And I still have this webinar control panel. Do you see the webinar control panel?
We do not. Only you can see that.
Okay, great. Okay, well, welcome everybody to this webinar. And I've always had an interest in what was different about desert soils than soils in more temperate climates. And my expertise, frankly, is in soils, is in areas of temperate climates. So a couple of years ago, I started being asked to make some presentations in the desert areas of the U.S., kind of starting with the ASLA show in when it was in Phoenix. And since then, I've met a number of desert soil scientists who I've learned from. Doug Merkler is one of the people I've met, and I've always been particularly impressed with his kind of hands-on, boots-on-the-ground approach to soils. So I thought it would be good to bring him his ideas to the design community, which is most of the people who make up the webinar. So we're going to turn this over to Doug. He's going to be giving most of the presentation, and I'm going to be chiming in with some questions or other things during and after the presentation. And we're hoping that it will be a little bit of a dialogue, but it's mostly Doug's show. So Doug, take it away. And do you want me to go to the first slide?
Yeah, if you wouldn't mind. Thanks, Jim. Well, good morning, everyone. It's a pleasure for me to be here. I'm still not seeing the next slide, Jim.
I am having a little technical difficulty here.
All right.
There we go. Can you see it now?
So, thanks. Definitely not seeing the forest for the trees is part of the story, I think, with soils. People don't think about soil very much, although we live because of it and on it. It's absolutely a ubiquitous component of our life. but we actually don't really think much about it, and we kind of have a negative connotation a lot of times. We talk about something being soiled or something being dirty, and we want to clean it and wash it. But in reality, soil is absolutely an essential component for all life on our planet, all life on Earth. So the question is, what is it? What is soil? Well, it's the solid fraction, minerals and organic matter, liquid, primarily water, and gases that are characterized by horizons or layers. And these horizons or layers are different and distinguishable from the initial parent material that the soil formed in, and they're there because of transfers and translocations of materials over time. And in addition to that, this leaves us with a material that is, number one, and important, three-dimensional, and two, it's alive. The density of organisms in soil is phenomenal and leads to this ability of soils to support plant life. So what is dirt? And Jim has kind of provided this for us. The dirt is a soil that's been put in a truck and is driving away. Well, certainly we've lost our three-dimensional nature in horizonation of a soil when we do displace it and put it into a truck or a wheelbarrow. So maybe we can think about dirt as being soil out of place. Might be a way to think about it. That doesn't mean it couldn't be mixed and used as a material that could still support plant life, but as a soil itself, as a three-dimensional scientific body that we would describe, it's no longer that. Next. So simply just the composition that we talked about in the last slide, that it's, you know, what is a soil, and it's the mineral fraction and the organic matter fraction and the water and the air. It's important to point out in this slide that we're talking about forest soils here. And when we talk about organic matter in this, we're talking about 2 to 5%. That's not a bad number for forest soils. But in the desert environments, in arid regions, that's optimistic. That's optimistic at best. And we probably are looking at 1/2 of 1% of organic matter being present in arid systems. The water can contain up to 50%. The porosity of the soil is the maximum volume that can hold water and gas. And so it's shared by those two components. And a soil that is completely saturated has all of its pore space filled with water. Next. So it's pretty important for me, I think, to develop kind of some boxes of how soils actually form and the importance in that. And so these are 5 soil forming factors that were developed primarily by Hans Jenny at Cal Berkeley. They give us kind of dials or rheostats that we can turn, with the idea being that if the dials are all turned the same, that it wouldn't matter if we were in Idaho or in South Island, New Zealand, that if all the dials are turned the same, we should end up with a very similar result and end up with a soil that is related as far as its physical and chemical properties and the interpretations that relate to it. So climate, both rainfall and temperature. Parent material, this is the source material that the soil will form in. So it follows and makes sense that a geology, say Paleozoic carbonate sediments, would provide a lot of calcium carbonate in the soil as it formed, and this happens to be very true. Topography, slope, aspect, and the geomorphology, or the shape of the land, that are very, very important also, as is time, which is really just the amount of time that a surface, a geomorphic surface, has sat there looking up at the stars. You know, it's kind of that amount of time, and we could define a geomorphic surface as a surface that occupies both space and time. And then the biotic factors, kind of the classical chicken and the egg. On the carbon and organic matter goes in, is related to the vegetation that's on it, the plants, the animals, the microbes, And a lot of times kind of left out is this us in the equation. And people are an enormous influence. And for this particular group, you're dealing with environments that are anthropogenic environments. These are cities, these are parks. And so the us part of the equation now is very large. Next. So as far as the climatic component of soils and formation, it turns out that climate is technically a part of how we classify a soil. So really, if we describe the soils in an area, we have in fact also described the climate of an area. And it's important to understand that it's not just the amount of rainfall that we might receive in a particular area, but that it's also really important for the frequency of occurrence and when that moisture comes. So we have areas that have 50 to 30% of the annual rainfall they receive comes during the summer when things are actively growing as part of their growing season. And others that it's the snowpack, and kind of a time-release snowpack, and green in the spring and then very dry in the summer. So this frequency of occurrence is very, very important and tends to lead to specific assemblages of plants that have advantages over others. Next. So for an arid climate, this is kind of a generic climatogram or a diagram that kind of shows that. And you can see that in the winter time, with not a lot of total rainfall, that we receive more rainfall than is evaporating through evapotranspiration, and we actually have a surplus. So in a sense, this is making deposits in the bank. And we finally reach that point where there's kind of the equilibrium, where the evaporation equals just the amount of moisture that's coming into the soil profiles, and then we begin to dip into the bank and we begin to make withdrawals. And that portion shows as green on my slide here for the soil moisture utilization. And those withdrawals that we are making then depends very, very much on the individual soil type and the texture of the soil, the rock fragments that the soil has. Those all affect the water holding capacity of that soil and in fact become the size of the bank that we can store water in. And then you can see we finally go banked up. And now, even though we may be receiving some rainfall, and in this diagram the bump in July and August is summer moisture, but the summer moisture is not enough from rainfall to even come close to meeting the evaporative demands, and thus we are truly, truly arid, and we have no water that is being stored in the profile at all until finally we end up in November, December, and we're back into putting some deposits back in the soil as far as moisture is concerned. Next. Yeah.
Might interrupt. In most of our urban landscapes, we kind of trick this hydrograph by adding irrigation. And one can see that we need to start adding huge amounts of irrigation to make that yellow soil moisture deficit go down. And I think one of the goals of sustainable landscapes in desert environments is to figure out how to reduce the amount of irrigation so we get to a soil that's functioning more like this hydrograph than an artificially changed hydrograph.
I completely agree, Jim. And I think that really becomes part of the realm of knowing your bank, knowing your soil, understanding the amount of water that it can hold, how quickly that moisture will be utilized, and then being efficient in developing an irrigation management scheme that adds just the right amount. Not more than you need that's lost to deep drainage, and obviously not less than you need, because then you suffer production and drought stress on the species that you're trying to grow. And of course, also then comes into play the selection of which species you want to use in your plantings, being adapted better for those conditions that you actually have. Or is that good? There we go.
Yeah, I think you did a good job answering the question. So we'll move on to...
So the parent material, the source material for these soils, at least most certainly in natural systems, kind of arrive as alluvial sediment packages. And they're different, and they are generally then described by the geologists in the world, and they have their different units that they describe. But this really becomes this source material, and it's not a soil until it has been altered and changed by processes that are soil forming factors that we saw in an earlier slide. Next.
I think you're going to lose this slide. There we go.
So, oh, that's okay. That's fine. So if we were to take a look at the regional geology in any given area that you're working, even within the cities, you get a valuable clue as to what the parent material is that you may be working in. This particular slide kind of illustrates the bare ground, the natural ground that's still there, and yet you can see the developed areas. And so the colored polygons is a single geologic unit that is mapped and runs as if it was on a bare natural ground. But we understand better than that. We know better than that. And we know that when we have developed neighborhoods and golf courses and buildings, that the upper portion of this at the very least has been changed. There's now a % of it that's asphalt. But nevertheless, understanding the geology that was there as a source of the parent material prior certainly gives us some kind of a hint or clues that we have to what the material below potentially is going to be. Next. The topography, morphology, shape of the land is enormous. Throughout much of the western U.S. at least, we have a very strong linear relationship between both moisture and temperature related to elevation. So as we go higher, we are cooler. As we go higher, we are wetter. And it is remarkable when you take a look. Go ahead and give me a click on the next. When we take a look at the actual difference in elevation in the southwestern region that we're living in the western region, the big gully that appears in that cross section is actually Death Valley, and you can see that it goes below sea level. So it's 282 feet below sea level, and the very tippy top of the peak is just about 12,000 feet up on top of Mount Charleston. That makes up the western boundary of the Las Vegas Valley. So this is over a 12,000 foot vertical difference in relief, and so we have this enormous gradient of changes that happen within temperature and for precipitation and moisture that are enormous differences. And so it's very, very important that we pay attention to the landscape, to the elevations. And even though this is a map of kind of natural landscapes, you have instances where you may have a rooftop garden that's 40 stories high on top of a building as opposed to the trees planted in the sidewalk down below. So even in a microcosm, these differences in relief and shape of those objects have a huge importance in the microclimate that exists. Next. Just to kind of illustrate this as an example, we can see the shaded side of the rock outcrop. That happens to be some Jurassic sandstone, about 65 million year old sandstone, and you can see that in the shade is kind of the northern face of that, and on the illuminated side of that rock outcrop is that southern face, and obviously that receives different amounts of solar energy, and obviously they have very different temperatures. And then you get to see the flattened surfaces that have both eroded and maintain some flat surface, and so the amount of energy that they receive then is also different. So even though we're talking about a natural landscape here, the mimicking of structures within a city, within an urban environment, certainly exist. Next. And so to summarize the importance of that, at least as far as the amount of energy coming in, the evapotranspiration, or the demand on the water that's stored in the soil, is hugely affected then by solar insolation on a surface. And at landscape scales, this is the major factor in distribution of the amount of energy on a surface, and variability of elevation and the orientation of the surface, the slope of it, shadows that are cast by adjacent features, strong gradients of difference in the insulation that leads to differences in evaporation and microclimate. Let's go ahead and go next. And here's an example to kind of show that. Here we have a north face on a mountain slope carrying a plant assemblage dominated by ponderosa pine, and we can see on the southern face bare areas of colluvium that are there, along with curly-leaf mountain mahogany and some scattered pinyon trees. So just the amount of difference in that aspect and slope, because the amount of rainfall that's received on this peak on both sides, the amount of snow in the winter, the amount of rain that happens in the summer, is essentially the same. However, the ability of the landscape to provide moisture, I guess, the water supplying capacity of the landscape is quite different. Next. This slide is here to illustrate time. This is very close to the Arizona-Nevada border, very near Mesquite, Nevada. And this is the Mormon Mesa. And this is kind of the granddaddy of hard pans in North America that we know of. This particular surface is almost 5.2 million years old that it has been sitting there looking up at the stars. And you can see on the upper portion of that, the B is for a brecciated or eroded layer. That's due to freezing and thawing. It's due to moisture and dry. And it's due to cool and cold due to solar insolation and the sun. And all of that lends itself to disrupting and breaking it up. A massive layer. And then the actual geology down below, where it says Muddy Creek Formation, now we're below any effect of the forming factors, and in fact we are back into the geology, not the soil. Next. So this material, throughout most of the West, we have hard pans, and in the science of soils we define them pretty specifically, primarily by the nature of the material that cements and binds them. But for someone working in a practical sense, the problem is now is that we have a restrictive layer that is restrictive for the penetration of water and roots. And so we have a very definitive restriction on the depth of soil we have to work with. So we can add more on top. We can try to disrupt that layer, as has been done here. And so it becomes pretty important to understand those relationships. Now, in a very dry area, it's at least conceivable with a moderate depth to a hard pan like this, and in a very hot and dry condition, it might actually be a benefit where it would trap water that would otherwise be lost to deep percolation. However, if it's only 10 inches deep or 15 inches deep, then we run into a problem, and the bank is just too small. There's not enough water holding in the soil to really be effective, to design a system that can keep it wet with the frequency needed to grow the plant species that we're trying to grow. Next. So that kind of brings us to the physical properties of soil. The profile and horizons we've already talked about. The texture of a soil. The structure of soil and soil PEDs, which are which are really a ped is the name of an individual unit of structure within a soil. The soil strength and its compaction and density, and then the soil water and its ability for drainage and its ability for infiltration. Next. But it's really difficult to look at any one of these without understanding the interrelationship of that property to the others. And in fact, they're very highly linked. We can't really talk about the density in the pore space without considering the texture or the structure. And it's very difficult to talk about nutrients and the fertility of a soil without talking about the pH and the acidity or basicness of the soil, because it's the pH that drives the availability of those nutrients. And so we end up with kind of this circular way of thinking, and all of this is woven, and the point of this slide I think that's very, very important is that many, many geologists and maybe others, they can consider a soil to be a rotten rock, but it's not. It's alive. And the intertwining thread through all of this then is the soil biology. This is the microflora, the fungal hypha, the life that lives within the soil is key to its success as is in functioning and providing the ecosystem services that a soil must do to be productive and grow plants the way that we would like them to grow. Next.
Doug?
Yeah.
I kept, in my explorations of desert soils, I keep hearing, well, you know, there isn't much soil biology out there because there's no water to support it. Could you address that concern?
Well, you know, it's somewhat a matter of context in what is a lot or what is not. There isn't any place without microorganisms. They are ubiquitous, they are everywhere. So even in very dry soils where we think we don't have any, in fact we have polysaccharide fibers from cyanobacteria that are binding the sand grains together and forming very fragile but important crusts on the surface of soils that are pretty sandy. UNLV research have drilled 3,000 feet into volcanic tuffs and pulled up those cores and had viable organisms in that volcanic tuff. So there just isn't anywhere without the microorganisms. They're always there. So it's really the story is about how much, how many of them are there, what's the density, and then what's the microbial ecology that supports that community, and what do we do that changes those environmental conditions that affects the ecology for those microbes is really the driving factor. That's the key.
Right.
Does that answer your question?
Yeah.
Okay, next. So soils are produced by the weathering of rock. It's a little bit confusing, I said, and I say, no, this isn't rotten rock, and then I talk about weathering of rock to form a soil. So I don't want to contradict myself, because the portion of physical weathering, chemical weathering of our rock parent materials is in fact part of the process. It's just not the only process. Constant exposure to wind and rain causes the rocks to break down into smaller particles, and it can take centuries to produce a fertile topsoil. In this sense, natural soils, as they occur on a landscape, are not really renewable within the time frames of our lifespan or many generations. Many of them take a lot longer to form than we can deal with in management scenarios. However, soils that are into an urban environment, a built environment, primarily end up being constructed soils that we make. And so in that sense, they are very renewable, and it just simply means that you have to go and get your mixture right and get your material right. But that implies then that you also understand the ecosystem services you're trying to get that soil to provide to your planting, and that they have been met. Next. So a simple example of just a couple of profiles, both of these are in natural conditions. One of them occurs along the Virgin River and the other one occurs along the Las Vegas Wash. So on the left-hand side, that scale is in centimeters. And I'm hopeful that it's clear enough that you can see that right around that 20 centimeter mark, there's kind of a slightly redder, has a more of a defined structured layer that is there. And in fact, that is a layer of silt that has been deposited on this surface, which is a back swamp surface on the floodplain. And so when it floods, it comes up on top and it will drop silt on the top. Below, probably below about 30 centimeters, we're in the coarser sands and fine sands, even though they're stratified. And if you get down right around 80, 70 centimeters, and you look a little bit to the left, you'll see what looks like kind of rust in the soil, reddish stripes. And you would be right, it is rust, it is iron oxide. And these are a result of conditions of reduction or being anaerobic without oxygen due to water. And so the key in this is that where those models are showing up is only in the root channels. So this definitively shows that this water that has moved through this profile is coming from a top-down scenario, which is only reinforced by the silt cap that occurs on the surface. But this would be important to know in trying to kind of understand the soil and the processes that were involved. If we go to the right-hand side, switching into inches, it's interesting to know that both of these scales, although one's in centimeter and one's in inches, are almost at the same scale. They're just about the same depths. We can see to about 16 inches on the top what appears to be this incredibly rich organic layer. That's absolutely correct. This is composed primarily of cattail roots. This is a terrace that used to be a cattail marsh. And so much of the carbon that was involved in the roots of the cattail are still present. And then down below, we have a silty texture. And we have, hard to see in this, but very subtle manganese and iron oxides again, but they're smudged and diffuse throughout. And this indicates then a water table that has come from the bottom up, and again supported by the cattail roots on top. So this was a kind of a true swamp condition where we had a shallow groundwater. Next. So this idea of the pictures we just looked at being kind of an individual unit. And we have clues when we look at this and we get a chance to have a look at the profile of the material, say, maybe where you're starting a project. You haven't added anything yet. But to understand the starting point that you have can be very, very important in saving money in the materials that you need to bring in, or in modification that needs to be done, removal of material that needs to be done. And so the more that you know about the conditions that exist in the natural soils, the much better you are in getting a project designed and having success. So we can see that these natural soils, then you have additions of materials, there's runoff and losses, we have translocation of soluble salts, of translocation of clay to horizons that are down below. We have additions probably represented on the bottom coming up, such as the groundwater, and then losses like deep percolation from water going through the profile, carrying with it those things that are soluble and forever removed from that portion of the soil, so they're now gone. This individual unit that we have, we call that a pedon as it shows up on the left side. It's important to understand that then a soil that we might map in your interpretation, say, of soil maps that may be out there that USDA and the Natural Resource Conservation Service and the National Cooperative Soil Survey has provided for most of the United States, is really the soil boundaries you look at are a collection of many, many, many of these pedons, and each of them being slightly different, but enough alike that they are the same soil type, and the interpretations and properties that we glean from that means that they're a little variation, but they're basically the same, and that's what we call a soil, is this collection of these polypedons, which then relates generally to a position in a landscape where it occurs, and generally speaking has a set of natural vegetation that would be tied to it that's unique for that soil. All of that gets disrupted in an urban environment, but the actual profile and the soils that are underneath generally remain until the point where we disrupt them and we dig them and we mix them, and then we need to know that difference. Next. So here we have an example of a disturbed soil that's been placed over a subsoil, and the upper portion of this is very, very compacted and dry. So it has been, now it's to the point where it's compacted enough that it's difficult to even get it to be wet. Undisturbed on the right-hand side, this is in Phoenix. The entire profile here is now friable, has low compaction, and it's moist because it's really it's easy and it's friable and permeable, so water is able to enter into it easily and retain that moisture, rather than on the left-hand side where primarily you're going to get a lot of runoff off that surface. Next.
And Doug,
yeah.
I actually dug these profiles. The one on the left side, which is very dry, is an irrigated landscape with drip irrigation throughout for each plant. But the space in between the plants is incredibly dry. The undisturbed soil, which is literally across the street from this first profile, hasn't been irrigated since it was in agricultural production the year before. So it's been a long time since this soil was irrigated, and was still moist all the way throughout the profile. So that's the big difference of what happens when you put these compacted different soils on top, and how that aspect essentially stops the normal flow of water.
That's right, and so it's not maybe just compaction from, say, heavy equipment, but it could also just be a difference in texture too, Jim, that can cause that to happen. And it's very, very apparent in looking at these photographs if you just take a look at the inner space between, and you see that the compacted dry soil is virtually devoid of vegetation, probably not helped much by a gravel mulch that's on top. And then we see the undisturbed soil, the more friable soil. Look at the grass that's been there. And that's not even irrigated. So that's a pretty dramatic difference. Next. So the texture is a big deal, we're finding out. This is kind of an important aspect of this. Many, many properties that have to do with the soil as far as us using it as a growing medium really come back down to texture. There's a lot of inference we gain in understanding the texture and knowing what it is. So when we take a look at this, the sands are they're ginormous particles. These are large particles, at least in the context of the others, and they provide kind of a structural integrity. One of the differences here you'll see is that we have a very nice sand fraction that's been separated out. So we have very coarse sands all the way down to very fine sands. And the very coarse sands in some systems actually fall out as being very small gravels, and the very fine sands in some systems actually fall out as being very coarse silts. So the sand fraction that we get is real important in the amount of very fine sand or coarse sands or medium sands. Generally, as a soil scientist, is something that I want to know. And I understand a lot of the tests that we run, they just give you the total sand. So if there's opportunities in the lab work that is done to request the sand fraction, it would be my recommendation that one do that. The silt fraction, then, is this smaller fraction, and now the capillarity of the spaces between the grains is just right for the retention of water. So the silt size fraction really is that fraction of the soil that is the very best at water holding due to adhesion and cohesion of water in the cracks and the crevices of those particles because of their size. And clay, the smallest of all. And clay, technically, is based on a size, but in practice, a lot of it are actually they're clay minerals. And they have a charge to them, generally a negative charge. And so they're very much a place where positively charged cations that are fertility in soils are bound and held. So they too have a water holding capacity. They have very small pores and sometimes too small, where they hold the water so tight that the roots can't extract water from them. And so they kind of have this hygroscopically held water that even though it may seem that the clay is a little bit moist, the tension that the water is held won't give it up. But very, very important for the fertility component of a soil. This is really where soil fertility happens, is in the clay fraction.
And as the landscape industry has progressed over the last 20 years, I've increasingly seen the specifications for soil to move in the direction of the coarse to medium sands in very, very high quantities, and the prohibition of fine sands, silts, and clays. And I feel that we've gotten way out of balance from a natural system, and it's that move that's causing us to have to irrigate more and more of our landscapes.
The lack of water holding, I guess the trade-off has probably been a high rate of infiltration and entrance of water, and permeability of water through a profile with the higher sand contents has been probably the property that they were chasing. However, you're right, as we lost silts and as we've lost the clay fraction in particular, we're taking away the water holding capacity, and we're taking away the fertility component of that soil. So that's a problem. Maybe an operational definition is pretty good. I know when I describe soils, there's sometimes when I get right about between 15 and 18% clay is really a good number. And that turns out to be just about the percent clay that you can take what you're texturing in your hand and throw it at the side of the truck, and it will stick to the side of the truck. Then you know you have enough clay. So if you take a little bit of a ball and you get it wet and you toss it at the side of your truck and it bounces off and it doesn't stick, you need more clay. Maybe a quick comment, Jim, on the gravels before we go.
Okay.
And we can need to do that. We don't need to go back. No, we don't need to go back. But I do want to make the comment about the larger fragments in the soil. They don't hold water. They don't hold any fertility. The structural integrity they provide at that point is really, it's a negative to the soil, because what you've done is you've reduced the volume of soil that's available for all these other properties that we're trying to get. So primarily the rock fragments can be considered a dilution of volume, and ideal conditions would be, if you don't have rock fragments, that's a better deal, particularly in a built environment. Thanks, Jim. We don't need to go back, though.
Yeah.
Sandy loam, topsoil, this is kind of how it looks. And you can see this diverse particle size. You can see the larger sands are showing up almost as white specks. The silts are going to be very difficult to even see, and you have no hope of seeing a clay particle. They're too tiny. They're so small. They're sub-micron sized. Let's go to the next slide. So if we take a look at a textural diagram, then we kind of come back to where this sandy loam is. And usually this variation of texture is very well illustrated in this slide, where this is actually kind of smudged in with the crayon. And so you can kind of see that we're a sandy loam, a loam, and maybe just up into a sandy clay loam. And that if something comes back in a report that you have done for a texture on a soil, and it says that it's a sandy clay loam, you need to pay attention to the numbers and see where it falls out on the diagram, because a sandy clay loam that's pretty just barely at the 20 or over that 20% clay is really acting very much like a loam, as is a heavy textured sandy loam is going to act very much like a loam too. So it's important to know that the boundaries are crisp boundaries that take you from a sandy loam into a loam, and that when you're near the line, that the properties of the things that are smudged in this crayon for these textures acts very much the same. So just because it may say a sandy clay loam, you need to pay attention to the percentages of the particle size and take a look at where they fall in the diagram, and that would be hugely helpful in making decisions as to what you need to do. Next. So,
against the time.
All right, so we're going to go fast. I'm sorry I'm taking too long. Let me see. The structure is really important, and is we have, these are the different kinds of structure that we get, and it has to do a lot with, again, the percent clay and shrink and swell and formation. The platey structure that's up in the corner, because of the horizontal plates that form, it tends to inhibit water going in. Granular is probably one of our best structures that we have as far as friable good soils. And subangular blocky there is probably the most common. Let's go to the next slide. So one of the ones in arid regions that's very common is a vesicular crust, and this is actually little tiny bubbles. You look at it and you would think, oh my goodness, look at all the pores, this is really good. Go ahead and hit the ticker again. But as it turns out, all the little bubbles are really bubbles, and they're not connected. So what happens is the transfer of water from the area in the soil matrix part into the open air of the bubble inhibits water flow. And these type of crusts can literally prevent water from going through right up to the point until they're saturated, and then water can flow through pretty fast, kind of like you would expect with that texture. But even though you may have a coarser texture, these are very commonly very fine sandy loams that would have a good permeability, the soil structure itself inhibits that. Next. And this is illustrated by a diagram from Hillel on the permeability of a soil and the rate of infiltration over time, and what happens once we do get a crust. Now the crust could be salts, it could be a vesicular horizon like we just saw, it could be compaction from equipment on the ground, but it's a loser in this scenario. More permeable layer soil is going to converge with time to a uniform soil, so we generally start with a really high infiltration rate, but as time passes, things will kind of compact. That's normal. But you can see with the crust, we're behind the curve literally, and we never really recover. Next. So the density of soils is very important and kind of variable too. So we start out with rock itself. I'm going to go from the bottom up, and rock is typically 2.65, so that's about like quartz, and most of our rocks fall between 2.7 and 2.4 somewhere. Concrete is 2.3 to 2.4, and it's important to note that the caliche layers, these hard pans that occur, run from about 2.0 to 2.2 and are just right there in the family with concrete. They're that hard. And then you see the soils, as it turns out, the higher densities on the soils actually occurs with some of the coarser material, and we get to a lower bulk density as we go up. And we take a look at forest and grassland soils, and we actually become almost less dense than water. Now the important thing that's happening there is that what we're doing is we're adding organic matter. It's the addition of that organic matter that is reducing the density of the soil material. And all of the benefits you get from the organic matter is in addition to the increased permeability and friability that you gain from that material being less dense. Next. Infiltration of the water into a soil is kind of intuitive if I have a sand that sits over a clay. That when I add water, it will go rapidly through the sand, and it will, and it'll hit the clay and it will perch, and it will. But what's not intuitive is the reverse of that, where I can have a fine textured soil, and in a lot of cases this happens when people mix soils or they do this in a built environment and they don't blend the boundaries. So they have abrupt boundaries between the materials. And here it's exactly the same scenario as in the vesicular crust, as we have very, very fine pores holding water under tension, all of a sudden being adjacent to larger pores in essentially airspace. And the water will not go from one until the other until essentially the fine layer on top is saturated. And then it will transmit to the coarser material down below. Next. Oh, you went one too many.
Yeah, I'm
I don't know.
There you go. Let me get this once and see what maybe we're here. Okay.
I want to wait a minute, make sure we're stable here. Okay, we're good.
We're here.
And I don't want to interrupt the presentation, Doug. This is so fascinating. I do want to make sure we have time for questions. Do you have a sense of how much longer?
We have two more. We have this slide and one more. Yep,
oh, perfect. Okay, go right ahead. Thanks.
I think I'll do this really quick so that we're not going to. This is an example. This was from a class that Jim did in Las Vegas. And so you can really see very well where you've added this composting mixed organic material on top, and you get to the surface where they graded it, and you can see the carbonate fragments are kind of floating, and it's an irregular mix with the organic material below. And then we finally get back into this compacted layer that's down below that. So this is a case where some of the response wasn't what they really wanted, and it was because they had these really abrupt boundaries that were not transferring water properly. And this is, again, kind of illustrated by the profile over on the right-hand side. Let's go to the next slide.
Yeah, but while we're on this slide, though, we felt when we were out at the site that what really needed to happen here was to come in with a backhoe and mix all those three layers, the fabric, the organic layer, the graded compacted fill, and the compacted native soil, just mix them together, and you would actually have a pretty good soil.
That is exactly correct. Yep. Yeah, it's the boundaries between them that was the problem. So the ability of that soil to provide water then, now here's this inches per foot. You can have inches per inch of water held, inches of water held per inch of soil or foot of soil. But it's the important thing here is that we have a field capacity and we have available water and unavailable water. And it changes by texture. And so one of the realities is that when we measure water in soil, so you could even have a good project and have a water sensor in the ground, and you're going to pay attention to that. What you're going to get back out of that is you're going to get water as a volumetric percent. And those are the gauges that are inexpensive. They're the ones that are available, and it typically ends up being the one that everybody uses. However, a volumetric percent of 20% in a loam and a clay loam, kind of illustrated where you would end up on this graph, you could have a volumetric percent in a loam where the water was available to the plants, but it would not be to the clay loam. So the number that you're given in the volumetric percent needs to go through a water retention curve and a conversion, essentially, to be able to understand the potential or the tension that the water is held under. I guess it's kind of like putting on glasses, and now you're looking at the water like a root would see it. So now you're thinking about what the tension of that water is, and if we put water into tension units, then we normalize the texture, and now we're looking at that soil in the manner that a root would look at it, and that's the right way to do that. Next. And this is the final slide. I'll let you and the audience read this. I hope it's if nothing else that the importance of soils has infiltrated a little bit into the group today. And it's been a distinct honor and a pleasure for me to be able to come and talk and to hang out and visit with Jim is always fun. And with that, I think, I don't know, Jim, maybe open it up for some questions.
Yep.
Yeah, Jim, why don't I'll just invite everybody again to submit any questions or clarification that they want. We do have a few minutes left. And while we wait for some of those to come in, Jim, why don't you ask whatever's on your mind?
Well, the one topic that always is interesting is the difference between organic matter as it's being tested in a laboratory and compost. And I hear people using those two terms interchangeably. And Doug, tell us a little bit about the difference between organic matter and compost.
Well, compost is, the best way I can think of that, I think, Jim, would be to think of compost as a precursor to the organic matter in soil. Material that's been composted properly, right temperatures so you've removed pathogens, and been in compost long enough that you have really truly broken down the organic constituents, the banana peels, the leaves, whatever they are, and they're no longer recognizable as a leaf. They're no longer recognizable as a banana peel. And then we have humic acids and lignins that really make up soil organic matter. They've been broken down by the microbes into huge long-chain carbon chains, and they provide huge amounts of available water holding capacity and fertility. They do both. They too act like the clay. So the organic matter is this end point kind of that you get, where the compost is a precursor to that. Microorganisms will flush, will have a population explosion a lot of times in compost. If people don't really understand or realize that, then they take that material and they'll put it into raised beds or they'll put it into their plantings, and all those microorganisms will literally steal all of the nitrogen and phosphorus that's available as part of this population explosion until it's all gone. And then when they die, their bodies release those nutrients finally. But in the interim, your plants have just had their dinner stolen from them. They no longer have those nutrients available for them. And we see that a lot where people will put on fresh compost. It hasn't composted properly, and it actually reduces the fertility of the planting bed that it's been put in.
And the other issue is that we measure and talk about soil organic matter as a percent of dry weight of the total soil, where compost is discussed as a volume, a moist volume in the soil. And so what I'm trying to...
and they're very different metrics, yeah.
They're hugely different metrics. So my recommendation is that in your specifications, when you have the word organic matter, only use it when you're talking about soil organic matter measured by dry weight, and then all the other things, if you're talking about a soil amendment, use the word compost. Do not use the word organic matter in your specifications for organic material that you're adding to the soil. Just call that compost or whatever you want, but do not call it organic matter.
We've had a couple of questions come in, so let me interject, if that's all right with you both.
Okay.
Yeah.
The first question is, when you speak of mixing the layers of soil to minimize the water boundary between them, is there any adverse effect to soil structure by disturbing those lower levels? Is there a point where disrupting the structure is more harmful than blending the layers?
Well, that's a really good question, and it's kind of an on-site answer for that. You know, my sense of it is that if you have really favorable soil structure, and you find that, but it's generally in the natural soil, the process of leveling an area and then adding, say, compost on top, that structure isn't there to disrupt. So it's going to be better to mix and remove a hindrance to infiltration, and you really don't have a lot of structure in place in this artificial material that you've put in. It takes a while for that to form. Hopefully that answers.
Some of that answer is what kind of equipment are you using to do the breaking or the fracturing? And my favorite tool is a backhoe, where you are just lifting that up and literally just lifting and dropping the soil and not trying to stir it up or mix it up too much. Just a simple lift of the backhoe, lift it up 3 or 4 feet, and then let the bucket drop out will give you the amount of mixing that you need. And you'll still have lots of really big chunks of structure left in that soil.
Great. So we've had another question come in that kind of is in the same area. So let me interject with that. Is the issue of soil mixing and how it affects infiltration rates a reason why it is important to mix the interface between engineered soil and native soil in a bioretention bed, for example, a stormwater BMP?
Absolutely.
We would both agree that the more mixing you can do of these layers, so you would ideally put down a small amount of the bioretention soil and then till it or scratch it with a backhoe. The problem that we get into on bioretention is that there's often a series of drain lines down there that make breaking that up difficult, but there are ways around that that particular problem.
Anything you want to add, Doug, or does that pretty much sum it up?
I think you know their question answered their question. I mean, I think they're right, and you know, unless you're trying to inhibit, I mean, all of these processes go both ways. So you want to kind of mix and blend, and it really means that you have a similar texture in an interface, or at least a gradual gradient, so that you get that. The other way of thinking about it is you might want to hydrologically protect something from water or infiltration, and so you put in a trench, and what do you put in? You put coarse gravel in there. And then you have this really coarse material in interface with a finer material, and it will tend to inhibit water flow into it until it gets saturated, and then of course it's going to act like a drain, right? And then it'll take all the water.
But I think the depth of the soil above is important, and what your goals are. So that if I'm on the East Coast where I get lots of rain, that saturation that Doug just described might be a problem. But in a desert environment, and this saturation doesn't last forever. It releases once the soil becomes saturated, and that serves to slow down the rate, holds the water faster. So I think you could also build a case that, especially with bioretention, that imposing that I'll call it a choker layer, because that's what the golf people do, may be a good thing. And in fact, if you look at the design of a golf green, they work very, very hard at imposing choker layers or layers to do precisely what we're describing will happen, where the upper soil will stay saturated for a short amount of time before it releases. So I think you could build a case in either direction, and for me, it's a function of how deep the soil is.
Mm-hmm. Let's talk a little bit about additives to the soil. We have a question asking, has any study been completed that discusses the effects of landscape additives, such as fertilizers, over time in respect to desert soils?
You know, the amounts in the soil that you're talking about, case by case, is very important. Again, if you add, obviously, if you add high nitrogen fertilizers, and there's enough moisture in an irrigation scenario that you're allowing for leaching of that, then you're pushing nitrates down below. Potentially, you're pushing them in the groundwater, and there's other issues. So the most efficient thing that you can do is to push additives that you want. And I'm assuming that we're talking about fertility and fertilizers. You want them to go right to the base of the rooting zone of the plants that you're growing, and no deeper. And that's going to be the most efficient, whether you're in a field growing alfalfa or you're doing a tree that has a healthy root system and you want to get it down to the base of those roots, but no more. You're using less water, you end up using less fertilizer, And so a very good fertilizer management scenario type management system is going to benefit and should be less expensive. As our resources become tighter, we should tighten that up.
The work that I think it was Hall did down in the Phoenix area, I think I sent you that image, and what she found, she was looking at suburban landscapes that had been turf and plants that were non-native, essentially lush green landscapes that we think of in the East. And those were being converted over to native plant landscapes with the idea of saving water. What they actually found was that the residual fertilizers that were put into the soil for the turf and these eastern plants stayed there and made the native plants grow so fast that they actually used more water, or just about the same amount of water as the turf did, at least until they used up all of that fertilizer. So the initial impact didn't give them the effect that they were hoping to get by using native plants, because the native plants just sucked up all that fertilizer and were in fertilizer heaven for a while.
Well, so we're getting close to probably the end of the timing of this webinar, so I'm going to go ahead and ask the last question now. In an urban setting where structure and organics may have been removed from the site, how long is the remediation process? How long does the remediation process take when using an amendment and breaking up the different layers?
I'm not really sure I quite understand the question, but
yeah, I would say that if you are physically working the amendment, working compost and physically breaking up the soil, the majority of the effect is almost instantaneous because it's a physical process that's being used to break up the layers. If you're talking about putting mulch or compost on top of the soil and thinking that over time that will change, there is some forest study that I looked at where they did that for 35 years on compacted soil, put compost on top, and they saw no change to the soil below. So just putting the compost on top of these degraded soils isn't going to do anything for you at all. You have to physically work it in with a backhoe or a rototiller or whatever device that you've got, but it's got to become integral to the soil, not just put on top.
Right. The lack of infiltration and translocation of water is going to be a problem, not just for water. It's going to be for anything else you put out there. So that's right.
Great. Well, Jim and Doug, I want to thank you both so much for taking the time to share your knowledge about desert soils with us today.
You're welcome. It was very fun.
Good. As a reminder, the recording of this webinar will go out later today. It will also be posted on the Deep Root YouTube channel. So we hope everyone enjoyed themselves, and we'll see you at the next one. Thanks, Jim.
All right.
Thanks, Doug.
Thank you very much.
Bye-bye.